Okay, so I'd like to welcome up to the stage Ken Church from Nscript, who will be telling us about 3D printed electronics are powerful when combined with chips. Thanks, Ken.
Okay, thanks so much for the opportunity. Congrats, by the way, to TechBlick and what they're putting together. They've done a tremendous job in moving some things forward. Let's see if we can make this work. So I think there's plenty to talk about when you start thinking about how 3D printed electronics can impact, I guess, the next generation of electronics. That's really where we're trying to get to. And so I wanted to talk a little bit about what's in a name, because there's been an evolution in this naming thing, and it'll probably continue to evolve, but eventually it sets. A little bit about 3D printed electronics as according to Ken, and what that is as far as what I say 3D printed electronics is, what chips means, 3D printed electronics demonstrators, and then some weird places we're going, and then we'll draw a conclusion. And so here's the question: why so many names? It started out and especially the TechBlick folks know this because they changed their name too, by the way. But it started out as printed electronics, and that was really not printed electronics. It really came from direct write. And direct write is really cool, except for one thing: it means really slow. And then there's flexible electronics, as those things start combining. And when it really came out as printed electronics as we're going. So 3D printed electronics started making sense because people understood printed electronics. And so layman's term for printed electronics, or 3D printed electronics, is really additive manufactured electronics. And so we said additive manufactured electronics is, of course, additive. That's sort of the point. And then it moved to what we call direct digital manufacturing, and that's the technical term. And so it just means more than additive. And so you can do subtractive or other processes. And then 3D manufacturing, layman's terms for direct digital manufacturing. And that's just it for you marketers, that you guys seem to like cute names, something that people can understand. I think that's where it went through. Chips, on the other hand, well, for those of you who are from the United States, you know one thing: it meant money. And that's all you cared about. That's all any of us care about, frankly. And so it really got down to it. The CHIPS program came out. It was CHIPS and Science Act, and it was billions and billions of dollars. And so far, well, not so much. And so we're still waiting for that to sort of roll down to the rest of us little people. Some of the big folks like Intel, they're starting to experience some of that, and where they're trying to expand that out. And then chips themselves, semiconductors, that's really where that is going and where that's at. And so 3D manufacturing, it's not all about just 3D printing. That's really where we're at. So I'm showing you an Nscript system, and that's one of several versions that we have. But it's just a lot of different processes in a single system, including pick and place. And so the question is, why would you do that? And so I think it's really about full automation, so that when you punch the button, I like the last speaker what he said, people don't want to touch this thing. They don't want to adjust this thing. And we have some customers like that. They say the problem sometimes is we have to adjust your system, and we're not super happy about that. And so we're trying to automate that out. And that's really where this is going, in full automation. But at the end of the day, it's many things in one system. And so also why we sometimes phrase it as factory in a tool. And so let's go about chips and what they are. For those of you who are from the semiconductor industry, you guys know front-end process really well, like really well, but you probably can't spell PCB. And the whole idea is these are very, very separate things that go on. And so the processes are very different. Front-end process, back-end process, PCB, and don't forget, for those of you who've been around long enough, LTCC is also something that has been out there for a long time and is now starting to make a resurgence. And we'll try to address that in just a little bit. But think about it. I love it how Apple does this. They're talking about 114 trillion transistors in a device. Now, I don't know if that means anything to you, but that's as big as the U.S. federal deficit that we have going. And so when you really get down to it, it just means it's a lot, is what it means. And so if you're going to print a transistor, we're going to be here like 114 trillion years before we can make one of those. And so we have to learn to work together is really where that's going. And so the same thing. And I want you to look where it's going. So they're doing 5 nanometer technology right now, and it's going to go to 2 nanometer technology. Samsung just announced that. They're going to start working on 2 nanometer technology. They're not going to stop, right? It keeps going. PCB, all these guys are very stubborn in where they're going. They want to thrive. They want to survive. And so it's a continuation of how that thing continues to go. All right, so where do we fit? How do we play? And it's really like you have to get to the outside world. You can have a transistor, but that's really small. 2 nanometers, I don't know if you know how small that is, but yeah, it's really small. And so it really gets down to this. How do you go from there to where we live? And so this is where the back end comes in. This is where PCB comes in. But here's the thing, though. As the expression goes, printed circuit boards and all these chip things are flat, but the world is not. And so we live in a non-flat world. And so how do we get out to this non-flat area that we live? And so we can play in that. And so my upper right-hand corner, you see me printing on a bare die down the bare die and then off. And okay, all that is a demonstration because you just wouldn't do that in real world because you create an inductance in that, and that's a little thing. So it's a cute demonstration, but it does show that we can print to that, which is very exciting. But here's the thing that happens. So there's other things, materials that you might need. Picture right next to it with the little red sort of material around that. It's a dielectric coating in that. It provides a ramp, but it also provides that dielectric interface that becomes very important. Lots of ways to do that, but here's where it goes. If you want to start stacking, if you want to start doing things where you say, hey, wire bonding, and by the way, wire bonding is going to be extremely stubborn, just like PCB. That stuff is not going to want to go away. But there are some issues with wire bonding. Speed is not one of them, by the way. Those guys are freak show fast. And that's just becomes very important to all of us. Remember, at the end of the day, we must compete. And that's really how it's kind of driving. So wire bonding, it turns out to be very fast in where it's going, but it does have its issues in the fact that those wires dangle, and then you start layering. We can't layer. Try the lower right-hand corner. Try to wire bond stack chips like that. That's not going to go well for you. And so there is room for us in here, and this is really what we're talking about. Lower left-hand corner, that's a 300 micron diameter fiber, I guess you might call it. 300 micron diameter, that's about 3 times your hair's width. We printed 20 micron traces on that were over a meter long. We did that at 800 millimeters a second, and we're printing to 40 micron pads. This becomes very clever, number one, but two, try that with wire bonding. And so it really gets to this. There are some applications, and again, the world is not flat. Not everything that we need to put electronics on is flat either. And so there's some enormous possibilities out there. Here's where else we play. When we start thinking about what's going to happen in the curved surface, and so putting electronics inside polymer is really kind of cute and clever. And if you think about it, FR4, what is that? That's kind of cute and clever too. That is not this rigid, some of these structures that we're talking about, they're actually inferior, and some of the thermoplastics out there are actually superior to FR4 in performance from an RF point of view. But the problem is, we still have to get down and metalize this. Our friends at Celanese, this is actually Celanese material that's on these things that we printed. One of the things that they have figured out that's really important is we must be able to, that must be compatible. How do we make sure that the silver that we're putting on, and why silver is right, so we've talked about that, lots of issues with oxidation copper. Copper can be cheap, but it also can be very expensive when you start processing. So at the end of the day, we're very good at silver, but how do I get the silver to stick to the plastic? And it becomes very important, something that we have to address. And our friends out there have done a very nice job with that. And so we're able to put some electronics together with this in a shape, and that's a cylindrical shape, and that was a 40 millimeter diameter shape is what that is. And the lower left-hand picture, what we're seeing, a phased array antenna. There's 7 RF functional layers inside that phased array antenna. And that is, I don't know if you know what that means, but it's really cool because it's RF, number one. DC, okay, pretty cool. RF, really hard. And especially when you start running higher in frequencies. And so now we're running at 35 gigahertz in some of our phased array antennas, and we're doing this with printed devices like this. So there are active devices under each one of those little patches in that blue cylinder. And so active devices are just what you'd say. So I've got to print to those active devices, and I've got to make sure this thing is rugged. And that's what happened. We have a paper coming out in a few months where we're starting to test some of the interconnects, and that's really where it's at. And some of the interconnects that we're seeing, we're experiencing 20 to 50,000 G. I don't know if you know what that means. It means you can stomp on this thing and it's still hanging in there pretty well. That becomes very exciting for many applications where it goes, because those of you who have phones, you can't keep them in your pockets or on your waist. You drop them a lot. And so those start experiencing things. And it's important that the interconnects survive, and that's really where we're going. So keep going is where we're going. There's also the flexibility of material choice, and that becomes important. Is material choice means I can make conductive things, but I can also make resistive things or heater things. And so why would you make a heater thing? Again, our friends at Celanese have put some heater material together, and when they do that, they make some very clever heater sort of structures, and I really like what that's going on. What we did is we printed it in a curved shape, and we did this, and I'll show you why we're going to do this in a little bit. But now I can start wrapping heaters around things that I couldn't before, and I can also make that structurally sound, and that's sort of has its advantage in that. So when you start doing these things, the most important thing that you have to do is control volume, and that becomes really a critical piece. So when we start controlling volume, if you're going to make an antenna, I got to tell you, those are pretty forgiving. A coat hanger makes an antenna. But if you're going to make some other things, like an RF strip guide, very unforgiving. Resistors, very unforgiving. Heaters, very unforgiving. So volume becomes very important, and that's the nice thing. The lower right-hand picture, what we're really showing is that we can control volume, and then you can change that. So you can actually change your heater over a distance if that's what you want. And so there's some clever things that Celanese does to control that, but you could also control that with volume. Lower left-hand corner, that's a 6-inch sphere, or half sphere, and we printed a metallic pattern all the way around that. And then we can actually bury that and then just keep going. So we can do multiple layers with that. I'll let your imagination go where you want to with that one, since I'm not really to say anything about it. Here's where we're going with this thing. You say it's a CubeSat. And so for those of you who love space, you know, they came up with their little CubeSats, and that whole idea was that we could rapidly put something together and then launch that at a much reduced price. And we did not live up to everything that we wanted. It is just now starting to move that way where it's getting, I guess, cheaper. But the problem is there are a lot of wires in a CubeSat. Those things open up, and it's like a spaghetti exploded inside your little box because you have all the electronic devices that you have that you're trying to shove in there. And when I say shove, I literally mean shove. And so trying to package that. So what we started doing is we started putting all of that thing inside the body of it. And then we could leave the rest of it open for payload. And so the lower left, and by the way, I just violated my own rules. It says base PCB. Let me make something very, very, very clear. We in this industry, at least right now, do not make PCBs. And so if you're saying that, you should stop, because we don't do that. We make printed circuits, and we can make them well. But when you go to somebody who makes PCBs, and they're used to bulk copper, and that's the standard they go with, and they go through their PCB designer, and they come out, and you make this thing, and they say, wow, your PCB is inferior. And the truth of the matter is, they're right, because your material is more resistive. And so we go against that standard. So here's what I like to talk about. So I didn't put this chart together, so I'll go back and talk to somebody about this. But here's what I like to say. We make great printed circuits. And by the way, the best material on the planet as far as conductors goes, it is not copper. You guys know this, right? I mean, so there are better and more conductive materials than copper. We could use superconductors. Why didn't they use superconductors? It was a little bit inconvenient is why, right? So if you're having to cool that stuff, there's some other things going on, they can say the convenient best material was copper, and then it became the standard. And then all of the designers learned how to work with that. And then everything is around that. Folks, we're gonna make a new standard. That's where we have to go. What is our advantage? Our advantage is that extra dimension. That's really where it goes. Our advantage is obviously no material waste. That's an advantage too. Our advantage is multiple materials. That's our advantage. Lots of advantage, but let's go back and remember, we are building an industry together. That's what's going on. So if for some reason you are my competitor, I'm still cheering for you, because this is a tough thing to do, as unfortunately, we've been doing this for a long time, and this is a hard nut to crack. All right, so over 1,000 vias, 257 components, 4 layers, and it's about almost 12 or about 300 millimeters by 200 millimeters is a dimension of that, and that is where we're going with that. We did print the box around that. There's solar cells on this thing right now. There's a payload in this thing right now. We're very close to the point of handing this thing back over to Space Force and moving that thing, and they're very happy with what those results are. But I think the bottom line is we will give you more room for your payload. We will put all the bus inside there, all the comms link inside there, and we put it inside the structure. Very challenging to do with traditional electronics. So here's where we're sort of going next. We have a system on the International Space Station right now that's printing biology, and they want to put electronics on it next. But they want more capabilities than just 4 heads. So we shrunk the heads, we doubled them up on some things. At the end of the day, we can get nine kinds of processes in the same footprint that we do right now on a single system. And it becomes very important when they start saying when it goes up there. By the way, it turns out they're very, very, very picky on the International Space Station, or at least NASA is on the ground before it gets there, about what goes up. Apparently things that float are not good. And so powder, not good. And so they're very, very picky about how this thing goes, and so there's some extra rules in how this thing puts together. But this is sort of, where we're at, and this is kind of where we're going next. Why would you go to -40 and print? Well, because they pay you. That's why. Again, that's why we're here. And so the DOD put out a thing, and it's actually public information, so I'm not saying anything I'm not supposed to. But they just call it point need challenge. And so we're going to print at -40 F or C, take your choice. And we're going to repair a circuit board. We're going to print a printed circuit structure. We're going to print a medical device, and then we're also going to print some kind of a mechanical device as well at -40. And so what's the point with that? It really is, it's all the same, right? It's just changing the environments. And that's sort of the advantage that we as an industry have, not just less materials, but really where factories are going. I mean, it's going to be really hard to compete with a trillion transistors. Obviously, that's true. But while that's true, it's going to be really hard to compete with us when we get our legging underneath us and how we can be portable. All right, so here's where we draw the conclusion. Why the space or the desert extreme cold? Again, it's truly distributed. It's the same tech. This is really what we're talking about. Printing is printing. Milling is milling. It's just how do we control that? All right, how do we move forward in this industry? First off, government partners are critically important. And so I would say if you're one of my government partners in this room, I am sincerely, my gratitude to you, and I'm thankful to you, because without that, we do not have the sort of the lift that we have, which also includes the honest feedback that we get from our government partners too. Remember, whoever has the gold makes the rule. And so here's the gold and here's the rules. And we don't like what you did, change it. And so it's really healthy for it in that relationship. Universities, I want to give a big shout out to my friends at universities, because universities are really important. They're also rather honest. And so what you want to do is you want to find universities and you want to find kind ones. And so go see Dennis talk in a little bit later this afternoon. Number one, he's a very creative guy, but he's also rather honest, but he's also very kind. And so our university partners are very important to us. Small companies, I want to give a shout out to my ex-CPL friends, you guys, who are super great company. But the thing that becomes real important is these guys are hungry. I mean, small companies are hungry, and they're also disruptive. And this is why sometimes big companies do not like small companies, because they're darn disruptive about it, and that can cause us some issues. Big companies, you make it real, okay? Until you guys get involved, it is us scrapping and scrounging. So if you're selling these, thank you for being here. We appreciate you. Horaeus, are you seriously getting in the equipment business? That is hilarious. Super excited to see where you go with this thing and where everything else goes. All right, thank you again so much for the opportunity. I'm looking forward to meeting you guys out here.
Okay, we have time for probably one or two questions from the audience.
It's here. So I'm from the equipment business, indeed. Should I understand that this kind of things you show today are just unique tools? You just build one or two or three or five, but there is no intention to go into a little bit larger volumes?
Actually, I appreciate that very much. And if I gave you that impression, then I need to get off the stage because we need to go further, right? I mean, that's really where we're going. We have a few hundred systems out there around the world. And so we're in Bangkok, Thailand right now, running 24/7, 365 with 75 systems right now. And it always goes back to that expression, how do you eat an elephant? One bite at a time. Or in the Bangkok version, it's one dot at a time. And so we're going to step into it and make that impact where we can. Same system, same process, but it's doing a very limited amount inside that factory floor. So we want on the factory floor, and so all of our systems are SMEMA standards, number one. We're an ISO company, so all of that puts together, so then we send that out there. But I'm not gonna lie, we'll configure this thing for you. We want to configure it how you want to see it too. So you get lots of choice in how, but it configures. It's kind of like buying a car. You want this or this or this. This is really where we're trying to go. So we're out there. We do see, when am I going to punch a button and inside this little factoring tool, that's out. But printing dots, printing lines, printing antennas, doing combination of things, that's today.
Okay, thanks.
Do we have any other questions for Ken?
Hi there, just hi Ken.
My copper friend, by the way.
Yes, and so actually a comment about that. There are PCBs that are being printed right now with in an additive way, and it's not that it will fit all the required PCBs. Today, people are usually using 1 ounce or half ounce sheets, which will be, let's say, half ounce is about 18 micron. And for many applications, there is no need for 18 microns actually. And as you go to printed copper, you can get into much lower cost and still keep the benefits. The issue is not necessarily the conductivity. The issue in most cases is compatibility with processes, for example, solderability, intermetallic compound creation for proper soldering, which you cannot get with silver, but you do get with printed copper. So I believe at least that we will see more and more PCBs that are being printed in the next few years. And, one of my comments to a lot of people is, why do they call them PCBs? I mean, if they are printed circuit boards and they are not printed, then why do they call it this way? So I will let you think about it or ask me later. Thanks.
First off, thanks so much for that. I would say this, though, you're right about something, and that is, all you have to do is add more. And so so when you start looking at your bulk compared to bulk copper, we're not there yet. And even though we're not there yet, it's really a design to manufacture rule back to the designers. And so I'm going to say, if we're not honest with these guys on the PCB side, they come back disappointed. And so when we start moving forward, being honest with them where they're going, whether it's widening the trace or adding more, whatever it is, or getting them to change their design, we get there absolutely. But as far as PCBs, I think we need to change the mindset of where we're going and move that forward.
Okay, thank you, Ken. Great talk.